Hi, I'm Son, and I present our paper From Images to Task Planning, How NLP Can Help Physical Reasoning. Robotic manipulation is often framed as a planning problem. However, despite being efficient, classical AI planning algorithms have not been explored extensively due to the symbolic requirement. This requirement can be relaxed by allowing planners to be probabilistic. However, a metric function has to be used as a stopping condition, which in turn might lead to error accumulation and not useful for long horizon tasks. Another solution is forcing discrete representations, therefore satisfy the symbolic requirement. However, training with any end-to-end framework will be more difficult. We propose to use vector quantized variational autoencoder or VQVIE to solve these problems. VQVIE maps an image to a set of vectors that are differentiable and represented by discrete IDs. We also propose to include a linguistic task to constrain VQVIE to focus on essential features. We consider a planning problem from an image x1 to xn. Our goal is to find action sequence a1 to n by an action model M that minimizes a criteria h. The state encoder GE used to verify the goal state in the latent space. The state encoder VQVIE samples latent ZQ from ZE via nearest neighbor lookup. ZQ is continuous and represented by unique IDs. This is useful to train VQVIE with additional objectives. Therefore, we replace the reconstruction loss with a KLD loss where we constrain the encoder to reconstruct necessary details according to relation network. The relation network is pre-trained on the clever dataset, which is a visual question answering dataset on spatial reasoning. To validate our framework, we present an oracular action model which observes and maps all the transition tuples to a graph structure. With VQVIE, we reach the absolute planning accuracy. However, this model is not practical, therefore we also investigate a stochastic action model. The stochastic action model is trained only on a part of transition tuples. This action data is different than the dataset that we use to train the state encoder. The main component of the action model pi samples the next state after applying an action to the current state, and it is trained using the mean square error. Our experiment is structured into two phases. First, we train the state encoder on the clever dataset. Second, we train the stochastic action model using another action dataset from the classical Black-Scholes domain. We wanted this separation to investigate whether the spatial reasoning features learned by the encoder is useful in learning transition rule. First, we experimented with training the encoder only with either the reconstruction loss or the KLD loss. Then we used the reconstructed images from the clever dataset as the image modality for the relation network. With the KLD loss, our encoder reconstructs images that produce a much higher spatial question answering accuracy compared to the reconstruction loss. Here the first row is the sample images from the clever dataset. Even though the model with the KLD loss results in higher reconstruction error, it is clear that spatial relations are encoded much better than the model with the reconstruction loss. Next, we investigate whether using KLD loss also enables an easier learning of transition rules. While training pi, the states in the Black-Scholes domain are still encoded by the VQVIE trained on the clever dataset. We then evaluate the accuracy using the bitwise comparison between the prediction and the ground truth of the next state representation. Because the state encoder does not observe the action data, we confirm that during training, the state encoder encodes a higher quality latent in terms of reasoning when using KLD loss. However, this improvement is not enough for effective planning. Under a more complex setting, pi has to perform better to be more effective. Our contribution enables us to construct a planning framework for sequential manipulation tasks directly from images. As a future work, we would like to improve the performance of pi and then integrate this planner with a motion planner. to realize these plans by a robotic arm.